Hey guys, in this recording, I'll be trying to solve this integral that I found on Instagram on a page called Black Pen Red Pen. He's a YouTuber that does calculus and he creates his own questions. Okay, let's get started. First, I'll call this integral I, and let's simplify this integral. And let's first find our limits here. So the limit as x tends to infinity of the square root of x over the natural log of x, well, this will be equal to, as the square root of x tends to infinity, that will tend to infinity, and as x approaches infinity, the natural log of x will also approach infinity. So this is in the form of infinity, and this is indeterminate, so we're going to use L'Hopital's rule. And what L'Hopital's rule says is that this limit, if it's in the form of infinity or 0 of 0, we can differentiate the top function and the bottom function. So this is equal to the limit as x approaches to infinity of the derivative of the square root of x over the derivative of the natural log of x. And what this is equal to is the limit as x approaches infinity of 1 over 2 root x all over 1 over x, and just simplifying this is 1/2 square root times the square root of x, and the limit as x approaches to infinity of this will just be infinity. Likewise, let's evaluate the bottom limit. Natural log of x all over the square root of x. This again is in the form of infinity over infinity, so we'll use L'Hopital's rule. Of the derivative of my upper function over the derivative of my bottom function, and this will be the limit as x approaches infinity of 2 over the square root of x, and this is in the form of 2 over infinity, which will tend to 0. So I can write this as infinity and I can write this as 0. And now let's work on our integrand, because our integrand is quite messy. So let's label this f of x, and f of x is equal to the derivative of sine of x squared all over 1 plus x squared plus x to the power 4 over 2 plus x to the power 6 over 6 dot dot dot. And let's just clear this up. So the derivative of sine x squared is cos of x squared times 2x, because I differentiate my outer function with respect to my inner function, that's cos x squared, and then I times by the derivative of my inner function, which is 2x squared, and then that's over. Let's clear this up real quick. So I'm going to assume that it is the pattern follows this here, x squared to the power 0, which is 1 over 0 factorial, which is also 1, so 1 over 1 is 1, which is my first term, over x squared to the power 1 over 1 factorial, plus x squared to the power of 2 over 2 factorial plus x squared to the power of 3 over 3 factorial, so on and so forth. And I can write this as x squared to the power of n factorial, so on and so forth. And how I can simplify that is the series of n from 0 to infinity of x squared to the power of n over n factorial, and this is just the Taylor series expansion of e to the x squared. And so f of x, which is my integrand, is cos of x squared times 2x over e to the power of x squared, and bring in e to the power of x squared on my numerator just requires me to introduce a negative sign in front of the power. So I'll write it here, times 2x. Oh, 2x. Okay. So from this, my integral I, which is the original question. So my original question, which I called I, is also equal to the integral from 0 to infinity of cos of x squared times e to the negative x squared times 2x dx. And if I made a substitution, let t equal to x squared, let t equal to x squared. If I differentiate both sides, I'll get dt is equal to 2x dx. Here I have 2x dx, so I'll let that be dt. And then everywhere where I see an x squared, I'll let that be t. So this is equal to negative t. And I'll also replace my limits. When x is equal to 0, t is also equal to 0. When x tends to infinity, t will also tend to infinity because of this substitution here. So my integral is also from 0 to infinity of cos of t e to the negative t dt. Okay, now let's integrate this. So let me pull up a new page. So let me just write here that I is equal to my integral from 0 to infinity of cos of t e to the negative t dt. And right now I have two functions multiplying each other, so what I'm going to use is integration by parts. And what integration by parts is a formula that says the integral from a to b of a function u and another function dv is also equal to u times v evaluated at a and b minus the integral from a to b of v du. And so integrating this, I have to let one be u and one be dv. So I'm going to let dv equal to cos of t dt, and then integrating both sides, I get v is equal to sine of t. And if I let my other function e to the negative t be u, du will equal to negative e to the negative t dt. And so using this formula, my integral I is also equal to uv, which is e to the negative t sine of t, evaluate it at my bounds, which are 0 and infinity, minus the integral of v du, which is negative sine of t e to the negative t dt from 0 to infinity. I'm just going to pull that negative out and bring it to the front, so this becomes negative 1. So I can just erase that there, and this just becomes a plus. And let's evaluate this real quick. So as t approaches to infinity, e to the negative t will approach 0, and as t approaches to infinity, sine of t will oscillate between negative 1 and 1, but it's a finite number anyways, so a finite number times 0 is 0. So 0 minus, and then let's evaluate at 0. So I'll substitute 0 in. E to the negative 0 is just 1. Sine of 0 is also 0, so 1 times 0 will also be 0. So this term cancels out completely, and I'll get plus my integral from 0 to infinity of sine of t e to the negative t dt. And what I'm going to do again is I'll integrate this by parts again. So same formula, integral of u dv is equal to uv minus the integral of v du. So here I'm going to let dv, this time let's change it up. So I have to let dv equal to sine of t. So v, integrating sine would be negative cosine. T would, sorry not t, u would equal to e to the negative t. Du would equal to negative e to the negative t. And so using the integration by parts formula, I becomes the integral from 0, actually wait, sorry, uv, so negative cos of t e to the negative t, evaluate at 0 to from 0 to infinity, minus my integral from 0 to infinity of negative cos of t times negative e to the negative t. My negatives will cancel out, so I'm just left with cos of t times e dt. And remember that this was I, because here I is the integral from 0 to infinity of cos of t e to the negative t dt. I have the same thing here, and so evaluating this real quick, this comes out to be, if I evaluate t equals to infinity, this will approach 0, and if I substitute 0 into each t, I'll get minus cos of 0, which is 1, so minus 1 times e to the negative 0, which is 1, so I just get minus 1, and then plus I, sorry, minus I, and then just move an I to the other side, I get 2i is equal to 1, I is equal to 1/2. There we go. So I, which is equal to my integral of 0 to infinity of cos of t e to the negative t dt, which is equal to 1/2. Okay. Thanks for watching. Hope you enjoyed that. Bye bye.